So I'll be talking about learning and approximate Bayesian inference in simulated reaction systems. Can chemicals think? Okay. So apart from the trivial, obvious answer that chemical systems obviously can think, because everything that we know is built of chemicals, I was more interested in this research in much, much simpler systems. So artificial chemistry in a well-mixed reactor without any kind of spatial effects, diffusion effects, anything like that. We tried to make it reasonably realistic. We wanted it to be, in particular, we wanted it to be thermodynamically realistic because a lot of artificial chemistries aren't. But it wasn't modelling any specific real-world chemical systems. So what we did was using artificial evolution. How many people here are unfamiliar with artificial evolution methodology? Excellent. Good, good. So we evolved systems which could learn to anticipate features of their environment from past features of their environment. So we found not only that, unsurprisingly enough, we were able to evolve systems that could do it. It's unsurprising because chemical reaction networks are computationally universal, in the same way that neural networks are, and lots of other dynamical systems. So we were able to evolve systems which could do this, and which had nice simple mechanisms, and you could interpret how the mechanisms worked simply. But not only did they evolve to do the task, they also, without having been evolved to do this, their dynamics were amenable to a Bayesian interpretation. I'm assuming that fewer of you are going to be familiar with Bayesian, the theory of Bayesian inference, than with artificial evolution and artificial chemistry. Can I just see a show of hands? People who don't know anything about Bayesian inference? Okay, people who know a lot about Bayesian inference. Okay, and people who know a little bit about Bayesian inference somewhere in. Okay, great, that's fine. I'm not going to give any kind of tutorial on Bayesian inference, but I'll lay the basics out. Okay, so this is a straw poll of familiarities. Artificial chemistries, everybody, yeah? Unfamiliar with artificial chemistries, fine, okay. That's fine. It's not that important. Artificial evolution, I won't explain our evolutionary process because it wasn't an interesting part of the study. ANNs, everybody know a little bit about artificial neural networks? Anybody that really has no idea what I'm talking about? Okay, that's good. Bayesian inference, I've mentioned. And finally, Shannon information theory. Now, I know some of you, because James asked, some of you were here when Daniel Polanyi was talking about his information agent formalism. So you may not remember exactly how it worked, but at least, hopefully, you'll be a bit familiar with it. And yeah, anybody who doesn't know how it works, you'll have a bit of a grounding in at least your local academic community. Right, so one of the things that motivated this research was that when people talk about learning, when they study learning in natural systems, they're normally talking about brains, right? That's the primary focus of cognitive scientists and other scientists who try and understand how learning occurs in natural systems. And they abstract it by the formalism, one of the many formalisms of artificial neural networks. But we know from empirical observation that multicellular organisms are not the only things, and multicellular organisms with nervous systems are not the only systems in nature that can learn. We can even observe learning in single-celled organisms. There was some work by Todd on learning in paramecia, which is a type of single-celled organism, where they can learn to anticipate electric shocks which are paired with light flashes. And these organisms, they're not just too small to have nervous systems, they're actually smaller than individual neurons, right? So it's obvious that learning can occur in nature without requiring all the mechanics of a neural network, of a brain or nervous system. That's not very surprising, because when you look at the formalisms of artificial neural networks, they're just systems of equations that describe how things change over time. And chemical reaction networks are also computationally universal. There are lots of physical things that have where the dynamics are similarly expressive to neural networks, and we should expect those to be able to display some kind of learning behavior. In the case of single-celled organisms, probably a lot going on with genetic regulatory networks. Incidentally, not the kind of chemistry that I'll be talking about in this talk. Rather than the whole complexity of a GRN with kind of discrete changes and nice stuff happening there, we're simulating something much more basic and simple. That is to say, a number of chemicals in a well-mixed reactor that are just reacting with each other according to the normal laws of chemistry at a constant temperature and pressure. A bit more realistic than some artificial chemistries in that all of the reactions are in principle reversible, except for some. Although the rate of the reverse reaction could be arbitrarily low. So some of them are in effect irreversible, even though they're in principle reversible. And that the reaction rates of the forward and reverse reactions are related not just by the concentrations of the chemicals, but they can't be arbitrary because all the chemicals in the system are assigned free energy values. And these are constraints that make the simulation thermodynamically realistic chemistry. I don't think you need to know in more detail than that, but if you're interested, they're fairly simple. I'm not a chemist and I understood it. So we conserve the building blocks of these chemicals. So whether you want to interpret these artificial chemical species as being polymers that are made up of particular monomers, like in DNA or RNA chemistry, or whether you want to think of them as being just compounds of different atomic elements, there's a building block, and the building blocks are conserved in these reactions. So mass and energy are conserved in these systems. So you can imagine one of these chemical systems, and you end up, once you specify what the reactions are and the rates of the forward reactions and the constants in the forward reactions, and you can work out the rates of the reverse reactions from the free energies. Once you've worked all that out, you can imagine you can just initialize it. You've got a bunch of equations that look a little bit like neural network equations, but they don't look exactly like them because they're a bit different. You've got a bunch of dynamical equations that just describe a dynamical system. You initialize it in some state, and it's going to go to some either cycle, or in the case of a thermodynamically realistic system, it's going to go to an equilibrium without any, assuming that there's no input that serves as like a kind of driving force. But we're modeling these systems as though they were agents, which means we're giving them inputs and we're giving them outputs. In quite a meaningful sense, you could object to my saying that they're agents, because the outputs don't actually affect their environmental dynamics in any very meaningful way. They're just, we've just defined some desired input-output behavior on the systems by fiat that doesn't arise from the chemistry of the interactions of the system with its environment. But from the point of view of, I guess we're viewing them as observers, perhaps, rather than agents. Okay, so inputs to the system modeled as these things called boluses, which for anybody who doesn't know anything about chemistry, like I didn't, a bolus is just a bunch of some molecules that's been dropped into the system. So it's a spike in the concentration of an input chemical. And the output of the system, which was defined as a thing that varied over time, was just the concentration of a particular designated output chemical. So thermodynamically open because there was all of the things could decay into these into implicit waste products. We didn't model the waste products implicitly, but as explicitly, and there was a inflow of a given chemical at a particular rate to allow the system to be thermodynamically open and driven, rather than just decaying into a kind of thermodynamic equilibrium state where I don't know if anybody here's, some people here will be familiar with results connecting thermodynamics and computation. There's a lot of well-known results that systems in equilibrium can't do any computation, they can't do any information processing. So that's why the thermodynamics are relevant here. We were hoping actually that this thermodynamic aspect would allow us to say something about the relationships between thermodynamics and information processing in this particular system, but we never managed to do that. Okay, so the desired behavior of these systems, we had two types of input, something that we called a stimulus chemical, represented here by the S, and a thing that we called a control chemical, represented here by the C. And the whole function of the networks, the whole desired function of these systems was, when a stimulus pulse comes along, anticipate whether a control pulse is about to occur or not with the level of your output. So you can imagine lots of real-world biological situations in which it's desirable to do that. And it's worth mentioning that this involves detecting a temporal association between different stimuli. So all anticipatory learning involves learning temporal associations between things, and this is no exception. Okay, so that's what I just said. And crucially, the same system, so it wasn't okay just for the system to always produce output in response to a stimulus chemical, because it had to behave in two different environments, well, more than two often, but one where the stimulus chemical was followed by a control chemical, and one, in this case, where there was never any control chemical. So the system's intrinsic dynamics had to be such that when exposed to this kind of past history, it evolved into a state, well, evolved in the dynamical systems sense, not the evolutionary theory sense. It moved into a state where a stimulus pulse produced an output pulse. If it had been exposed to this in the past, its state would change to a sort of state where the dynamics meant that being exposed to a stimulus pulse did not produce an elevated output concentration. This is the simple example. So the system has to learn whether it's in an environment where these black stimulus pulses are always followed by the grey control pulses, or it had to also produce the correct output in the environment where you never got any control pulses. You can imagine that's quite a simple thing to do, and yes, it is. It's really easy to evolve a network to do that, and I'll talk about some interesting properties of this task later on. At least I think they're interesting. I hope you will perhaps think they're interesting as well. Right, the main example that I'll be talking about in this presentation is one, rather than learning whether there's ever a control pulse, so is there ever any control pulse? If so, then when there's a stimulus pulse, then I'll elevate my output, otherwise I won't. In this example, pulses always came in pairs. And either they were usually stimulus followed by control, with occasional control followed by stimulus pulses, or vice versa. And in the first example, where generally stimulus was followed by control, the network was expected to follow. So this target output was supposed to be high when it received a stimulus pulse, or stimulus pulses generally followed control pulses, in which case the network's output was expected to be low when a stimulus pulse occurred. You will be thinking, I love it when people say that because it's almost never true, you will be thinking, but at this point, the system's got no information about which way round it is when it receives the first pulse, so it's got no, there's no way in which it can produce a correct output. That's true, that was too bad for the system, tough. The fitness function I'm not, so for instance, in the case where Richard has got his jacket stuffed with two-headed coins, I have an unchangeable assumption about the world that if he's got lots of two-headed coins, then the chances are better than half that when you flip a coin, when he flips a coin, it's going to come up heads. That's just an assumption. Bayesian, the maths of Bayesian inference doesn't tell you how to make those assumptions. It just tells you how to reason consistently once you've got the assumptions. So like classical logic, it doesn't tell you what premises or what conclusions you should start with or come to. It just tells you what conclusions you should come to given the premises that you start with. The conclusions and the premises that you attribute to a mechanic system that is supposedly mechanically implementing Bayesian inference, those are up to you. That's part of your attribution. And also the initial probability distributions that are assigned to the environment, so its initial belief, as well as its assumptions about how the world works, those are all attributed to the system by you. So this is very, very Dennettian in a philosophical sense. It's very much seeing a kind of cognitive phenomenon as being something that's not intrinsic to the system. It's intrinsic to a perspective that allows you to attribute it to the system. Okay, so what we did on our holidays, we evolved these chemical circuits. They were able to, in inverted quotes, learn. That is to say, they were able to produce appropriate behaviour that depended on the history of their sensory inputs. The mechanisms were very simple, chemically speaking. That network that I showed you with all those reaction paths, actually not all of those are necessary, right? We could have pruned some of them out and still had a network that would do the same thing. It just evolved that way. And crucially, this is the thing that I'm interested in, we were able to observe the information storage, most of it, that allowed the system to do that. We were able not just to say, well, here is a mechanism, but we were able to say, here's an interpretation of this system as a reasoning agent that allows us to pluck a probabilistic belief out of its state. So that's a kind of that's a higher level cognitive construct than simply a belief about whether one thing is true or another thing is true. We're also plucking a measure of uncertainty out of that as well, in a way that allows us to interpret this system as doing approximately correct Bayesian inference. That's quite a big deal because that's what people like Carl Friston and other kind of Bayesian neuroscientists, that's what they claim the brain does. It does approximate Bayesian inference. In fact, some of them claim that's all the brain does. Obviously, this chemical system didn't do anything nearly as interesting as what brains do. But the fundamental principle is there. The kind of the jump from one to the other should be one that is quantitative rather than qualitative. That is to say, it should be possible to construct systems all the way in between, fill an entire spectrum of how complex they can do this kind of inference. Okay, so I think these are interesting questions for discussion. You probably have even more interesting questions to ask, but I think they're important and interesting. This one is basically about the fact that just because something's doing Bayesian inference, that actually doesn't mean it's doing reasoning. because you can implement mechanically, you can implement an electronic circuit that does Bayesian inference about something and then doesn't produce any output. So you just come in and you stick a kind of voltmeter onto it to determine what it thinks the external world is like and how certain it is about it. That, to me, is not a reasoner, because to me, reasoning is something that we attribute to agents who actually interact with their world in a way that we can consider purposive. So I think this is an interesting, this is an important distinction to make. It's an interesting discussion to have. Yeah, this question about whether mechanically implemented Bayesian inference is just the same thing as information acquisition, in which case a piece of paper is a Bayesian reasoner because it incorporates information about, what pens have been near it in what respect from its history into its current state. And I'm not convinced the answer to this is necessarily no. It may be the case that actually, yes, you can interpret everything as performing or implementing Bayesian inference. But then when you start asking questions about what it's performing inference on, you may get out answers that are just not very interesting. Well, that's such a, when we put it within this context, when we pose it within this framework, the description that we get out is so convoluted that it's pointless. It's not a good description of the system. So we can describe it as performing Bayesian inference in the same way that, we can describe a particular cosmic ray impact as causing the Battle of Waterloo. But that's technically causation, but it's not the sort of causation that we actually want to pay attention to or be interested in. I suspect the same thing may be true of lots, not just of Bayesian inference, but lots of cognitive concepts. That you can attribute them to just about anything, but very often the mileage that you get out of doing that is zero or negative. And then finally, another thing that I'm very interested in, which is there are strong relationships between information theory and thermodynamics, and there should be relations between thermodynamics and Bayesian reasoning. So this is to do with the relationship between thermodynamics and cognition at heart. I think that ties into things that autopoieticists say about cognition, because the process of autopoiesis only makes sense within a thermodynamic context. And again, you've got these people like Carl Friston who make more specific claims about the relationship between autopoiesis in the sense of something that sustains itself in a thermodynamically non-equilibrium environment. So the relationship between autopoiesis and cognitive mechanisms or cognitive interpretations of the system. Okay, how are we doing for time?
Finished.
Right, thank you very much.